Hello, good morning. Ngadu dile ani ngaju nima sumbe ki ani tamshe sigin re rolling di gonzu che chowa che shuen yi ani drink jushi di zo ani du gi sangwa dan jewa yodewa de la du zambala ani sedu ngom ribe ki namsha dan jewa yodewa ani chi tedan derche an nangbe ki shung nang la shebe ki du tarab ki nelu du tarab ki rotang 대가나 시다 지게 뒤참모다 세두기 남샤든서 계자시 용도 삼발라 따줍단 대화 여비게 주시 배차나 유유진 kin 대화 세야소론데 대가나 시 시제기 안에 직된 감게 춥지기 차 차슈든서 아니 요로 요단 칸데스 요레스 다디 아니 고 유진라 마되비기 아니 유기네 룩세지 요레다 요마레 아니 여비 임베나 칸데 요레스 매비 임베나 안에 유진 그 나올라 나완다만다 나데야든서 낭수든서 칸데시네 투구여레 낭수다 네수 발라 체버 카르카리여레스 야든서 기케자 레디유요 손자 안에 페주 낭덴라 롬니르 칭킹암 따딜라 토나 윤킹키 아니 kinbo 망부지키 토나 쳔부체 디시키 다 주시 롭센직 비차디여레 제가 안에 담시 칭킹 당부디 아니 게 조지 무스 차디여레 게라 코라이 메나 제다 세리키 아니 좀 팅켄인데 세리키 내주 사쇼카 나로라 아니 따 지좀 팅에 된데 차디 요리 이나야 아니 세리키 내주 약보신기 요베기 겸zel 때네 ngazuki leshi mangbu knanglola korangi gengol tuschiche ani nyamshu chenyong ke jire. So I hope that the translators are translating in the introduction part, so I'm not going to repeat that in English. So I request first presenter George Musu to give your presentation. So that's 20. Kamut nishu jilutes rotring gotsu sama konda shuen.
Thank you very much, and thanks to all of you for coming. Let me amplify and echo and share in the expressions of gratitude to all those who have helped to organize this event, make it possible, make the entire program possible, because what an amazing thing this is for all of us. I would also like to extend a special welcome to our students. Hello, students. I'm delighted that you're here, and in fact, afterwards, if you have any questions, I'll be free to talk to you outside. Anyone who's too shy to ask questions during the Q&A, I'd love to meet you. So today I have two surprises for you. The topic at hand is the nature of matter. What is the material world? What is it made of? What are we made of in material, physical terms? And it's a huge question, so I'll take a small part of it and ask, what is the nature, the basic nature of the fundamental ingredients of the world? Loosely speaking, are they particles or are they waves? And actually, let me clarify that a little bit. I had some really good discussions in front of the posters 2 days ago about this very question. So what I mean here is the category of particle and the category of wave. These are categories that in the Western philosophical and scientific tradition go back really to ancient Greeks and probably before. And the philosophers and scientists were working off our daily experience. What is our daily experience of the types, the basic types of objects around us? And to simplify, they identified two categories from our basic experience. One is the category of a particle, a bit of matter, a thing, a physical thing that has like this glass has a place. It has certain properties. It's shiny like a glass is shiny, or has a shape like a glass has a shape. Crucially, with particles, you can count them. Here we have 1, 2, 3, 4, 5 glasses on this table. The other fundamental category is, here I call it waves. But what I really mean is there's something filling space, something continuous filling space, like a fluid, a medium. In physics, we say fields. Magnetic field, for example, is actually around us. We can't see it, but it's filling the space around us. And it's continuous. You can't count it. And in that medium are waves. And the waves in this categorization constitute the material objects around us. So particles versus waves, this is the debate that we're having. So one important aspect of that debate, maybe the most important, is how do we know, right? How can we tell which of these categories, how do we know really anything in our knowledge? And this is something we all in this room study and wrestle with in our daily lives. We have, of course, our powers of reasoning. We have the prior knowledge we bring to a situation, our powers of logic and thinking that we can apply. We have our senses. We have our scientific instruments, which are really amplifying or extending our senses. They're taking the world that's maybe invisible to us directly and putting it into a form that our senses can access. So, I'm pleased to report that in this room, there are probably hundreds of sophisticated scientific instruments. Our phones. These phones are filled with magnetic sensors, air pressure sensors, sound sensors, and light sensors. In other words, your camera. So everyone take out your phone. Everyone take out your phone. Even the students, please. If you have your phones, I don't know if your teacher lets you. And look at the back of your phone, at the camera. So underneath in my case, there's plastic, then there's the glass, and underneath that is the light sensor. So the light sensor, what is it? It's actually, in this phone at least, in most phones, it's about 1 centimeter square. So this is actually about that big, a little bit smaller. And depending on which phone you have, it's divided. This one has 50 million pixels, 50 megapixels. So 50 million boxes, like chess squares, that the light is broken down into. So think about what that means. It means that the light falling on your phone is divided 50 million times. So this is giving us a kind of microscope into light, in this case. We can maybe analyze the fundamental nature of light because we can divide it into such a small amount. So everyone go to your phone and go into the camera app on your phone. So this little experiment we'll do has two steps. They're both quite easy. First step, zoom as much as you can. Get as close to whatever. My phone goes up to 8x. I've talked to my friends, they have 10x, I've heard 5x, you have 5x, 15x. Just zoom into something, doesn't even matter, anything. Okay, step number 2. Put your phone, it depends on where you're sitting, maybe put it on your armrest of your chair, put it on your lap, put it on a table. Okay, you should see I've done something like this. I did it with my phone in the hotel. I zoomed it and put it on the table. No, notice, I don't know what you see on your phone, but what I see on mine when I do that is it looks grainy. It looks pixelated, right? You can see little teeny things flashing on your phone. And normally you don't want that, right? Normally you're trying to take a beautiful picture of the sunset or your friends or whatever, and you try to eliminate that grainy quality. But now we're going to look at the grainy quality. What is the grainy quality? Why does your phone create that grainy image? There are actually many reasons for that. But one of the reasons, actually in some circumstances, the most important reason, is that light is particulate. It's like rain. Imagine rain falling onto your phone. We had the rainstorm the other day, right? Rain was falling on the ground. It falls here, there, the other place. Hail falling. That's something like what's happening with your phone. Here's a basic picture of what that might look like if you're actually looking at your phone kind of on the side. What's happening? The rain, the photons of light, the particles of light are falling on the phone, hitting it, and throwing out In this case, electrons, which are particles of matter. So it's actually, your phone is a way of turning one type of, or at least energy of one type of particle into that of a second type of particle. That's what we think is happening, and it's consistent with everything we know about science. So you can actually see particles on your phone, or not actually literally the particles themselves, but the evidence of the particle. That is what in physics we call, or in engineering, if anyone has studied electrical engineering, it's very common, shot noise. Shot noise. It's particle noise, really. It's the noise that comes from the discontinuous nature of whatever is striking the phone or whatever. Now, I've done this program only twice before, and like many of my colleagues who've been here several times, I've had the honor of doing it twice, and both times we used a solar calculator to demonstrate another way we know that the world seems to, or the ingredients of the world seem to fall into a particulate category. Now, the solar, I haven't brought one here, but the solar cell on the calculator is a light sensor. If you put it in the dark, it won't work. If you put it in the light, it works. And what's crucial is the type of light you put it in. You put it in red light, it won't work. You put it in green light, it will. And Albert Einstein showed that that is evidence for a particle nature of light. Then there's other things you can do. Let's bring our sense of touch into it. What happens when you do that? How does it feel? Hot, right? Heat. What is heat? There's been a long philosophical and scientific effort over the centuries to understand what is heat, and our understanding now is that heat is the random motion of particles. So when you do that, you're taking the energy of your arm and putting it to the energy of the particles. You're making them move around like that. And that doesn't work if matter is continuous. It requires a particulate matter. But some more reasons. Here's another one that made Einstein famous. It's actually hard to see in this video, but on the left are actually a microscope image of little, I think it's milk droplets and suspended in water. And they're hard to see here, but take my word for it. They're moving around like dust in the air, moving around randomly because they're being hit on every side by particles. Here's a fun one. You can actually see particles in what's called a cloud chamber, bubble chamber. It's actually a type of detector. You know how in the sky, when an airplane passes overhead, it leaves a trail? Those particles are leaving a trail in pretty much the exact same way in that detector. They're going through the detector, leaving trails. My colleague, Professor Goulet, actually has an interesting experiment, again with your phone. You can actually use your phone. You actually have to put a piece of tape over the camera, but you can use it as a very similar kind of particle detector, and you can find her afterwards if you're curious how to do that. Another way is you can actually take pictures. You can look at the particles, in this case, at the atoms. Now, I have to clarify, these are not the atoms of Buddhism. These are the atoms of chemistry, basically. But you can actually use special types of microscopes to see the individual atoms. Some companies have actually spelled out their name in the atoms. The particles seem to come in different, what I'll call a hierarchy. So the atom, the molecule, also, is the basic unit of chemical reactions. It was actually also once thought to be the basic unit of everything. But then later, humanity, realized that the atom consists of subatomic particles. And then it turns out that some of the subatomic particles also consist themselves of particles, so subatomic particles. And there's a whole variety of those types of particles. That is another discussion altogether. I will say, however, interestingly, that the material world around us is mostly composed of 4 of those types of subatomic particles. So the number 4 comes up. The electron, 2 types of quarks, and the photon. So actually pretty much everything we see can be explained by those 4 types. But I did promise you a surprise, and promise you 2 surprises, so let's get to the first. And the first is going to require another extremely sophisticated scientific instrument. I think pretty much everyone in the room has even 10 of them. You will require your fingers. So what we're going to do, let me show you what it's going to do, and then we'll do it. you're going to use your fingers to create a slit. And we're going to use that slit to look at light. And what you should see, what you should be looking for, I should say, are lines that would be between your fingers. You can see it in kind of that circular thing. You'll see a series of lines like a barcode or waves coming onto a beach or something. In fact, that's quite analogous to what we're seeing. Okay. You can use many sources of light in this room. You can use the light coming in the windows, but we have prepared for you, due to the kind graces of the camera crew, a light. So what you're going to do before I turn the light on is take your fingers. This is the way I do it. Different people do it in different ways. I take my fingers like scissors. Everyone do that, scissors. And imagine doing that with their scissors. Then, to control it a bit better, take your other hand and put it on that. So what you're going to do is use that to press down and out and control that slit. You're then going to put your fingers close to your eyes, as close, and then open up as little as you can. And look for those lines. You can use, again, the different light, but this is actually a great way to do it. If it's working, but it's not working. There it is. Yay. This is very good because it's such a concentrated light. So go and look at something and see if you can see those bands. They're a little hard to see, but control your opening a little bit, make it come down, make it go, I got them. It looks like a comb, right? It looks like a series of lines. One eye, yes, I'm being bad. Linda, who's the expert on this kind of experiment, use one eye, bring it up to, maybe close one eye, bring it up to the other eye, like this, and look at that light source and look for that banding. I got it. Screen's light. We got, you have your selection of lighting sources in this room. You have 20 different lighting sources. You can use this one, that one, these ones above. Screen's the best? Who uses the screen? The screen's good. And I apologize to the students in the room. I know you don't have such good lighting in there. If you can't see it, perfect. If you can't see it, do not worry. Find me during the lunchtime. We will make it work. This thing that you saw, this banding like a barcode or just bands, is the diffraction, what's called a diffraction pattern. Here's another way that you can do it. There's me in my kitchen, by the way, with a candle and 2 pencils. This is what we did in Gang Talk a year ago. And it's actually quite a good way in a classroom to really make this work. It's a little bit easier than the fingers. But it's the same idea. You use the pencils like fingers. And you get, by the way, you get on the right side, see that banding? That's the sort of banding that you get. And in this case, it's actually colored, because that's part of the phenomenon. Diffraction is a wave phenomenon. It's suggesting that the category of wave is how we should be thinking about light, or is one way we should be thinking about light. Because it's caused, as these water waves are caused, by the ripples in the wave lining up with each other or not aligning with each other and creating patterns like this pond. So we kind of have a little problem here, don't we? Earlier, I gave you all this evidence that the fundamental nature of matter falls into a particle category. Here is an example of how light, at least, falls into a wave category. You can do the experiment in other ways with material objects like electrons. They too fall into a wave category. So what's up? How do you do it? Contradiction. Sa. Contradiction. Nature. I've contradicted you. But no, right? The contradiction must be in us. Nature is not contradictory. It's our understanding of nature that must be somehow contradictory. Our categories of particle and wave or particle and field seem inadequate to nature. And this is the contradiction, the insight that quantum physics just tries to describe and to some extent to explain. And I have wonderful colleagues who will describe many of the the puzzles that come from this understanding and that the quantum physics presents to us, because this contradiction creates all sorts of puzzles and paradoxes, and your mind just starts to explode. And that's really cool. Surprise number one. Two contradictory categories, because the wave and the particle are not the same. They're contradictory. One's in one place, one's spread out. Here is one way, and there's many, that this is manifest in our scientific experiments. Unfortunately, you can't do it without your fingers. I'm sorry. So suppose you had that diffraction pattern, or a similar pattern between your fingers. There is an example of it. I've blown it up so you can see. And you begin to dim the light down. You turn the light down. It goes to dark. Everything dark, dark, dark. What will happen? This too will go dark. That's not what we see. We see this. Start with the same pattern, turn it down. What's this? It's dissolving into particles. Here before us is a wave pattern and a particle behavior together. And the other esteemed colleagues of mine will walk you through some of the meaning that has. But I did promise you a second surprise, no? Are you ready? Yeah. Let's imagine a bunch of particles and you start to take them away. Oops. You start to take them away. These particles are going away. They should be at least. Yeah, they're going away. Bye-bye, particles. Yeah. What do we have now? What do we call this? We call this it's empty space. It's called a vacuum state. Empty, right? And in this kind of metaphor that we're using. So, I should say, be careful, that if the particle category applies to the fundamental ingredients of the world, and there are no particles, there's nothing. You have no objects, you have no activity of any sort. It is pure emptiness. I'm curious what you think about that. But in our theories, in our standard model of particles, we call it the particle physics theory, and in our scientific experiments, we actually observe this. It's empty, no particles, but look at it. It's filled with activity. It actually turns out the vacuum in physics is the most active thing of anything. And yet it's empty. What is creating the activity? One might argue that we have the particle category, we have the wave category, neither is working here. So maybe there's a third category that we don't know about yet. And that is my surprise number 2. Thank you.
아니 gen George lala 아니 투지 체스 슈이 제가 아니 지게 제등원 감릭 바 knanglola 아니 지게 두그 장신시야다 랍그 장신시야 아니 랍두 강양 매베게 동상기 반항기 나올림베나야 아니 자와체밤 아니 저와체베게 아니 지게 칠레딘데 아니 통야요베게 니수골라 빼고송송 디젤라다 제와든 정좀 문tun리로와 아니 디젤라 아니 nga tamshi baniwadi ani geshi tabgelodula chagiyo sabe chane gishilagi ani tik nangbe shungni shebeke ani du tarabda ani dinzuki ta nedang dinzukola she ta tedanyamdo ani gishila jurungbo ani sedung kamrikbeki ani keje shetan dinzo ani gyui imbeki jumzentene ani dini sungjerki samno tangdang khandis yumeta dinzo tola 아니 tamchichire 아니 계시다빌라
yes okay that's 직된티 시데테베 공살라민 남전 장고 제왕부 초라 구장원도 당내 안는데 페베 점내 긴두기 대당 안에 초자와 상말로리야다 참디슈 다디네 투즈 매원인자 갑동마 고축샤나 삼스 다 nga khasan jushi de kama ge songya chena ta nangbe shunggi dugi namsha de zu des shena si tangbo de da uchire ina ya ta ya jela kari shena de gre so ta khanda nge chi khasakane chi lens cheje en tuwa chinjushi de sma shua bezu shui ro 다 ngaran din nalo la jushi chidang chena zawa migi dirsa da uchi sumyu nangbe chungne shewe duden gi jingong gi domshi da sujun she da chikche dine duden sena kare se ya chikche di duden ko la ngazo chawa de duden ko la jeba chene kare pendo yore ngazo tujen so gu mare kare chige yore se ya che en tama de la ya da chik tingsan cheri gi nalo yudan yujeng de ko tal mixe chedung ngam cheri gi nalo chig yong yore di ko la ya samju de se da chikche na tumbo yosare 다 당기 다 세리기 돈의 제비나 고 가르치고 그래서나 로다 되서 된기도 와 당한저 때에 매자 중나당아디 곰튀고서 삼삼대죠 당한저디 건조기 유제 처대 한저기 다 제곰다 조금 지야 디송자 아니 다 오늘 제나 곰자고 해야 저래도 되다 곰잡되나 된 가면 저좀 당으로 하시 딕사마래 때만다 제가 다 이내래 다 단다 gangi 튀어지 되게 그래 세리기 돈에 뒤기 남샤도 간데 시에레스도 주제 배제당 안에 그 니레 초연당 당 시에레스 다 오늘 간저 직 시에야 되죠 주제 철라 당고 니람당 드링시에게 요르베스나 디아 마레스 코람 직 가리 요레스나 시제네 숨 세야다오당 직 유일라 시제네 숨 제야당 데네 직 간저 가르서 그래 따조디 덤바시 남샤 철라메든 가서 간살메든 철라든 세야당 디렉 돈에 안에 고비게 배제당야데 랑중 그리고 실라 소바 다디 배주 제변당로 주의 시제당로 주레야라 아니 ngaran주 주숨게 댄스고 디안 대원이다 더 도스체네 제 칼라간점제 신조레스 다디 신도 주제나 시제네 더 코비게 앙단데서 댄라 밥두고 말이디 지용게 남샤제 가젤레기도 남주 색초 그래서 저다 당보딜이야 다 genjo지라 송바나시 직제나 간저 단다데서 돼야 되죠 한람 다 얌첨부 쉬브제게 이제데 직제나 양 간저라 카시 닝바 인시 그래서 고서적에 베나 공불루도 기타도블 콤베 틱젠바 시게 뭔가 리과 사바디다 동네지 남사바 튼서 투미지기 요바 통 툽시드 양 카시 얌차보도 된데 답베나 된데 용시 버레스 대가나시 가브레 체리게 당기 갱게 덤바나시 라비앙레 뒤야인베 시드인베 소레 개와인베 소로 대세 잠마투바 돼야 되죠 가브레 체리기 딱제 심죽 체니 된게 요래라 가브레 낭베 리글람 페저 다용데 대세 잠마투베 내다 남바 코랑게 낭고레 리글람 피게 되나 줌제유베 소레 데데나 줌제유베 소레 줌제니게 바루랑 겐두 도제 ngobenelu kanlaya yang gendu imbe sonde de yanya yores 다 시당 낭주랑게 제장 ngaranzo da shedang de karesna da jungshigi duidang de so shegi yorwas jungshigi duide so shegi yores da yinaya nubjo nalo la jungshi du gor chedang ji shebina nangamo ge da gris da dwa ge da rub de so re tengrab ge chashana da zaze da di tone du thame tone de she jago re da de so be karso re ningba da ujere seya de ji le de yores da da koran yinaya kabri shib zabo da yone de chagi yo mares 단다 간주기 두탱게 남샤 셰야 되죠야 직 다스 사두 메두추도 오 메두 망고 쳐나고 메차도 그래야도 대세 디지고기 저기요 말했어 그런 게 나로라 대세마 십다 도연데 잘라 아니 직 뉴바당 첼레당 아니 제두사당 딘데 돈에 대세 망고 시작이 요래 스페셜샤난디 낭베 춤다게 따좀 가시 다 제라마에 춤다네 용디 잘라 정말 뭐부 첨부되죠 간데스 주비요나 디 총르 당제 대럽게 세르게 따당 나시체네 따둑게 토네 삼로당제 제요레스 디 제연데 안에 담에 따둑델랑한조 제두사 삭두 안 두두세두 땡사 제비나 elemental particle the atom the molecule 디게 따다도 제레 요레스 제단다 디존나로 트리워지 간조 가리티요레스나 두덴테조 간갈로 마뚝뚝뚝뚝뚝 나다 탐에버 두비야 요레 간잠진네 두그레스디 다 제라마에 tum다 제나 참해질로 톡구그레스야지 다 아니 계지기 이나다 가리나 다디 간에 용거레스도 장래 나란조 간사 소소라 나나스 슉첨부 슈 라연데 지도 바지래야 나스도 장래 도와지기 저거 나를 옆에 처나게 간지 시켜와 나시 치르기 쳐라 따연데 숙쟁게 ngo본데서 자장을 갱 랜드직 제나만도 알레 더 제리베 가르치나 디직 제가 저 왕가 제리 보니자 더 제가 다 속쟁게 쳐도 직탁다 도도 타마딜라 다 밥사직 고그래 삼야데 네 간에 연구열에서도 최담제 랑경원에 주고 거래 템바 주고 타르동네 제나 다던 제니 니사지 고그열에 삼야게 삼로디 요와 인자 다 두된 참에 계직 참에 타르동네 제나 딜 투고 그래 삼야 네 간에야 망시딩니 중결에서 다 이내 디저 티와 나로라 까브레 아네 두덴다 니기 파루레야 다 단다 때나다 베디네 차잔 자데 까브레 디저 두덴 디저 춘 자요나 똥바레요나 디바루 가레요나 디네 쪼바 빼망 보죠요레스 때 쪼바 디저 까브레 어다 디저 다 가스 쪼에 된게선 디레요 마레스 딩랍 제릭 나로라야 빼차잖아 만조 잘라디 딜라 투고요 삼고요라 오네 투고요르베스나 제릭이 따두고 터네 투마도 셰 투고요 마레 할람 투고 마레 랍투 가이스나 타마 마마레 온도 장라 두텐라 투용 lokdu 통 lokdu ni 바루 통 슉 잠네 비자 잠네 타마 톡톡 말해 제단다 디조 딩랍게 때비나래 어디 알레 오네다 도구면도 왔어 나랑 정에만 셔야 돼야돼 nga 동두 안에 nga 도세 동배 카도라 nga 육디 nga 레야 투그레 투그 말해 마통나 다 가르쳤네 다 그래 랍도 누가 주네 다 그래 라고로 다 대가랑 건조 세력이 가르쳐 라고 그래서 디 바루 lokdu 니디 독스 대요바이나 lokduini matuwaina lokduini barulan dewa karchen chigo resedu kabre udu tane kabre lab tane en dide dewa chigo re labdu duden leya ani dewa chinye gi duden 시제 두둑시체네 연제 당고야 데게 남샤망 볼레데요스 제가 응마게 수준게 따줍데도 차장로 세티보랑 맵이네레 갑조데 너르게 매바데 제베 고 갑조데 가왈레게 요바데 양안조 도스 톤투 그래 해삼고도 따디네 두댕게 세시 템베체 다 두댕게 세시데 오제 단다 간조 둑스마 템베체나 세르게 토네 두댕세야데 춘주 체연데 안가조 낭베 슝네 갈라 간잠직 체투요레 원베 슝네마 penang jakju rebon lokdan la nyesri du da soma dan se ya tak ngomba zwe de le ya shen da men da ge cheju shub ji yore nge samna gari yore sna namsha gari she ba di sugjen ragwe to ne khung shi ge gre khurang ge ba zo ge penang anju duten ji re la na tharma di sorchik si du jang la che se ya yo sorchik se se ya yo du sorchik le du ga ja yo me dang ga ja yo du chamo de ga ja yo me anju ang ji jap cho cha bre 내가 나시 ngomba zwe na la ke ba ji ja du jang la penang anju di la ge wa 가르사 안에 땅 안주 nendu luge야지 가서 단다 대시 자기와 땅에 책대랑 도마서 갑도 되려야 남지 두고요나 갑도만 제가 뒤치도 잘라 꼭 깨바 있는 로 가져 지자 딱다 지자요 고네 슉바르 깨바 차바네 뒤차바네 똥베 바르 뒤 차장지 대시 잡도 강가 남샤 안주 텐데 켈린 두고 유메 미시디 좀시디 할레베 차창고요 제가 뒤지기나 안주 지자 두고 다 단다 뒤지자베 원도 담비나 낭베 슝네 셰베 두 타랍 라비아 디 세리기 토네 셰야기 간저 다 가르스고레 두텐스 애톰스야 딜레 테즈 타워 메나 삼삼다오지 이나야 테랍기 세리기도 딜레 충아 하장 기타 곱두다 디조간라마 도투고요레 띵간저 남샤디 띵간저 켈랭고 고 딘데기 토네 이나양 디 중네 티와 가리오레스나 디 간저 가리셰당레스나 지라모당 도데베 셰당 두 참메기 셰당 시제 뒤래야 충슈지 요래 니네 잠고 레세야게 좀더 오메셔다 다 이나요 디 저거데네서 됐어 제가 다 딜래야 두된 참메라 가봐 당고 자야되죠 로베 아야 되와게 시작부터 나라 계시 두된 자네 거럽에 차체야 맵이나 잡단 뒤 용기 말에 되네 고바주 산에 보신기 말에세 딘데 셴네다 마 가고 잡네 두텐스야데 베데 가두이나 차체주고 그랬어. 뇽달라야 아주 삼로 따위나 콜로 샬로 눕장게 차체고 그랬어. 베 두텐이나 강가로 차단 제고 그랬어. 안 딘데체네 시자 탐제베 차단 제코 차단 차시 뜨베 데와 툼네 덴데게 남샤 둡다. 어 덴데 송요 그랬어. 다 디네 아주 디와지 가르차고 그랬으나 디 가란 줄라이도. 오나 다 툼다 고멜룰레 두텐도 총르 따네. 두야 자니요 말베스. 바데 가제 총르 따네. 디 딘데랑 멤베 소리도 먼저 따두게 삼로 토네 소소 삼로 가제 땅 투베 디츠기 자시 그 투베 러시아기 자시 직켈랭고 직대 가래서는 뒤 총르 따나 타르 누뱅 오두 그랬어야 단다 개인기 때야 등에 제가 등죠 말다 개인기 디나로로 동바차 두도 뒤에서 담아 제 랍게 오첸 디 가래서는 나란저기 디레샤 바도에 도나라 딘데 송도와 페나차샤나 군가오 페나 취향 착발 주네 착발야 줄주바이 최저라 되시 세컴 락바데 사시 첨부 줄도 참모네 세뒤 참모네 뒤 타랍디 파르도 줄도 시테틱바체 속신도 타웨 타르도디 차 뒤래 주바이노스 지당 안저 저저 나라 차 듬바 아니 안저 오바 단다디 노와 나라 죽바 아니 둥거 나라 차 제바 땡에덴스케 메바 덴데르 바코 인도장라 kungawas kede du tarab dini gobe nangba tongba juna nangba tongba le sugi namba chuba juro stati danda takda lawyagi kesi du pe chungshe de zoya meba soya ge tapsi taina ngwe nejula sobe ina ko tongba rangshi nube ngo dugre seya sonde namga tongba ngo dugre seya sonde che donala thende do jadanda di kor de shumoga che 다 디네 ngazo duke korte nangbe duke korte disamre besana tsane mares nangbe duke korte la ya pena du tuk ma tuk cheba cheba pardon yo ma yo to cheba chedo na do shu do chera ma esana tukya tsane yo mare pardon yo res dia ngam serik da dizol tuya do jigar do de sewa ina pardon yo ba ina tongba di na lo la we da dizol zu du gru was de yin tsang le tongba yo mare tukya yo mare su 야 뒤에다 대절에 딩랍게 찬네 제바 빼만 붙여야 그래. 먼저 의도지 도와 있나 의도다 뉴트리노스에 대해서 가르치는 누구여서는 뒤 코란래야 록뒤 쿠르메니 차지라 그러와. 차지 매비나 코 도에 가도래야 오버 셴발 견자게요 말. 다 당기 먼저 야 쿠르 연전이 요이나 토고고요 말다. 너 갑래니나 시제 담라레바 잠기 펜주 비자 따르 제야다 그 남샤데 톡도고요 그러와. 제가 딘데 망보다야도 내가 나시 나웨 뒤 문베 뒤 근데 다 전화를 망고 채도와 디조 오늘 전에 직전에 땅아서 수준 그 돈에 막고 와체 문바세야 돼서 뒤에 잠저래 삼네 직 좋아래 양당 오늘 등산 거라 다스타 배직 아주 직게자 알아서버려 셔있는 등산 시에비나 다크 매터스야 도다 다크 에너지 수도 장래야 직 딘데기 보관 나보다 딘데기 남샤 망보 나로라 뒤기 남샤 직래 거래 콘소 간데 두고 유맥 제가 딘데 게자 시에버래 왜 딘데 직래 야 봐봐 도메기 숑나로라 넘버 로가 직 시에비나 야 뒤세야 돼서 다 왕부 뒤 디조 다 지당은 저 나로라 다메타라 두제 제스 디강래야 아니 왕보다 디조 뒤자나 줍시다 근데 차도 그래서도 왕부 뒤다 디조 직남셔 셰고 야 바바 도메기 숑카셰다 디조 나라 최기제제기 뒤 최기제제기 송아 디조 나로라 야 뒤뒤다 뒤망보직 셰고도 먼저 뒤그 콜라 빼 할레베 단다양 베 눕적과나 시체네 konzo기 다와나 시 먼저 숑로 나로라 슈부다야 요바다 오지 단도야 여바다 오지 다 자상 간다 외베 내줄라 딩럽 나시 젠던 두고 메메셰디 뒤기 남샤 단도 망보 여바체 셰고도 삼 다디 남베 숑기 뒤기 남샤 잠제 오나 뒤기 오 가르세야지 당 아주 수중이 나로라 당기 갱기 나와나시 뒤스나 투야 여된죠 닌 독스 동가 잡이나 고 란싱기 직 파츠 파래야 윤죠 딘데 장발은 문제 지금 여러 요 말했어야 돼 제가 단단 아주 나외 뒤레바 문베 뒤 파바 도메기 차이나 의뒤다 부디 중화 제를 두바 말했어 중화 찍을 두바라 말했어 데 중화 찍을 두바래 만도 중화 뒤세 제가를 두비어 말했어 시생 알아서 그 뒤세 제세야 돼 제제비나 아니 드라이 카바나 티 뒤세야 도다 저 간대 체네레스 누베토네 드세 자기 요래 아니 오늘 람비게 찍마 세나 로가 티베제 가보르다 딩럽게 세리기 도네고 베시포르스디 마 세비나 딩럽 세리 도네 타마 마페베이나 시대 좀 시직강을 봐병 거 딘도 양 알아서 저바저야다 요래 빼나 차잖아 알아서 룰라 분바디 가웨 녀렌 두그르베스는 누구 말이디 시대 뒤원에 또트베이나 분바 소야게 제디기 뒤텐 애톰 대조게 코카와 소야를 베죠 땅에 요래 타메기 디 애톰 다도 제이나 가저기 녀렌기 뒤인데 페버베스 땅세 땅이나 땅에 유시바요 가웨 분베 녀렌 치바 요르베 거기 제준데 그 제준 오 누구도 와서 시대 뒤기 강을 파비나 누구도 와서야 다 대조 간제 가저 제바치야다 빼망고 요사레 삼고 아니 제리 코라 나로를 갱게 나와나시래 뒤시야데 당보 사정 예전 임바 지기 툭나 파래야 윤조 딘데 지글 삼로 땅에 어디 다 단다 딱제 심주 망보 랍임베 남샤 망보 땅에 뒤시야데 담도니 녜만나시 멤버 딘데 땅도 제가 다 디게제 시안도 아니 나란주 둥고게 나로라 남게 뒤 세야데서 강가로 인지 미지 숙제지 고기 매봐 고바 지 뒤 단데 숙제게 라베 쳐디게 바직 바팀니 아니 누뱅 오 껴르두스 숙제ng 오라 트야 윤조 딘데라 뒤기 남샤 지기 요베 선다고 딘데 레온 것도 제가 디조 직제나 갑죠 디조 얌사보레 삼거도 디직 쳔바레 제가 아주 둥거나라 차샤비나 남게 뒤 동베 뒤 내가 나시시야 제가 디올라 타마델 단다 닐스 보르기 직 랍도 everything we call real is made of things that cannot be regarded as real. Nganzo ki tanda thong debe ngobo sukjen raba kanga chik sa sing tekbe number shuji yo deba samsam di shite zomshi di pa zega du du zang le ya chik Koran chik lab ki sore tham do nye sore kabre tongbe ngon do nye de dinde chi che du zang la chik ko bige shite zomshi di chik dire se zugu zugsa mebe sore chi. Raba o di chik shina samsu. Da di jab che. Chezang da di ngaranzo peji chik shungi nalo la namde ki shungi nalo la wangbo dezo sukjen ki chene sungme la doya dang yang la yang chu nube ngo churja karsa suk ngo pyoya yoba sungbe sodawo ngombe nalo la wangbo dezo dui sungbe sodawo nganzo uman jubba nalo la ya ane rangi namshi tenji nui te la wangbo sukjen mikje chawar dosi labya dezo le yondi tat pete Einstein ki namsha geda shimbo nuba da doze ngon doya yosi ya dezo kabre chik chena dabu mena sam tadu ki chane sigi orda ko namsha ki chane shi ke sigi omar shize ki rabzam chik dabu mena sam ba chik dos ta dine shuya dire ta ona nganzo du ki namsha dezo kande res lavina tseri ki du ki namsha la durwa ina kon reshe jadang ta ina nganzo ki tadu ki chade mando shirum ki chade kabore tseri ki nalo la du tamu chik la nuba khaze yume ko ki ngone chik lo da chik shuk khaze tegi yume 안고 가제 dom나 가war레기 유메 니도 치도 항상 14보 열어와 디 열에 디 제르기 개베레 먼저 다두기 돈에 딘데 치투비아 거래 요마르 럽저 지금만도 다 이나요 제르기 돈에 오나 딜라 때네 먼저 메셀라 랍자 가르레야 요래 메세기 제당 랍자 가르레야 요래 디 항세르기 돈에 요마레 공오보 거라비게 주제다 디조 돌라 제야데 마도 지래야 디 가르제네 계기 요래서 라이나 베나 남바산제와 오나 뒤콜라 주도 딘데 제네 가르치고 그랬다 뒤타르도 가서 당고 네 가서 계시 때 가서 이시도 제 다세 담번 나시리 디 심부 탄제 방엘라 가에 녀고 메스 레베스나 딘데 마르다스 디 가서 가르치고 그랬으나 알레 딘데 제레도와 딘데 인도 네로라 칸데시 샤르게도와 준두 네 transi디 칸데시 제게도와 딘데 제도 나한테 칸데 제게도와 델라 때네 알라 도샤 셰당 칸데 용고도에 딘데스 용도 장라 간주기 타마데 가와 그랬으나 냠랭게 토라 삭버드다 뱅고 바발루두게 단다 디나라라 기부사미 추마이 미밀롱미 난가미 남시 마이 꾸메나 텔레시나 기부칸 기부캄 중 두베스 양다 마이체 디신 캄네레레 양 두이치 양다 니 마이스드 타마 아네 캄게 타마 사주 멜롱레레바이나 대양 세비나 가바 두그레스 파탁된젠 데네 제제제 안도 잘 알레 당한주 남주 잠데야 딘데 직 민도와 캔사와라 사미야게 삼주디야 제온도 신행 안주 다 알레 즉 나란쪽에 남주 짐바나시 빼나 강아스테 슈 요셈 데야 되죠 안오네랑 삼바나시라 요사 마르와 사미야게 삼연데 나쪽에 추 가와레스나 데 덴중다 다 다음에 받아 메다베 고아니엘라 빼나 뒤 담모 되죠게 제제 땅에데 당고 직된 섬속에 단통야미도 뒤 충슈에 되죠 가시에 로데 까르자 세겐 슈부 된데 담모나로라 다가런 직도 그때 배지직 가르서 오래 깔짝 가자 자세 담모나라 직도야 도 다야 저바두다 뒤 되절라 때는 메다베 남샤 제위나 단다간저 보디세도 포턴세지 디야 냠구도야 요 말쓰고 빠데 야 빠데 로추 정마 깨바 망고 된데라야 칠로기 숙제 마테베이나 요자네 메바 레베스 띵 간저 깨지기 요도야 디 요레다 요 말에 디 딱베 랑시 인다 마이세 간저 가르소레 치료베 중나로라 뒤 딱베 남샤시도와 디 항상야게 디도 등사지나 제릭나로 저바요레 포턴세야디 디게 요레 요 말레스 냠구 코란 중기다 되게 디지도 뒤 참모된 나가면 직된 감 정보 줍디기 보디디 단대 보디디 가라 레스고래 디디 갑레 코 텐도 딱바다 이미 미시디 내가 딱베 랑시지 셰요 되버래 양 먼저 메슨 뒤다 드롭 콜게 되죠 제나 세튼디 슈지레 되어라 양고 미다베 랑시 슈지 삼로다 유디 먼저라 디기 토네 따두기 토게 랍잘래야디 슈지요레스 디 인상 먼저 두댕기 토래야 주도 제고 개게요레스 두댕 토래 주도 제야 되죠게 먼저 가리시엔 두고레스나 오벤넬루 딜라데네 낭로를 잘해야 돼 먼저게 낭로기 유쟁 짐바 칸데 제기도 딜라데네 제야 디 제도 장라 딜라데네 가란조 용초다 당지 제지디 디 체릭 발라 메바데레스 다디 제도 딜라데네 먼저 타마데 가르치고래 다디야 즉 요레스 대바자 많이 받다 딩랍 가르치고 그래서는 다 지나 동반이 곰이나 근데 가야 제니 니주메베 따줍 된서 곰바이나 아니 루심을 요아 가르두고도 해서라 다 등상 가서 랍쳐져 매래 건조 뒤제게 내용 거와 다 뒤제게 내용 듣자라 다 가서야 딘데 그 딱제 심죽체네 단다다 디조다 신행 고쪽 바래 베나 단다디 딱제 지기 갈라브레스나 딩랍게 템바니샤게 곰데조 슈위직다 다르잡친데 여러와 이내 단데조 슈위직 단다 십자보 이메 메시데 좀쇼 가시 나로라 동니 고미야데조 직체나 템바니샤 곰발레장 만조직 다 가르소레 심감 트레덴다 데조라 펜체와 유사르다 세야게다 딱제 심죽 신행 고쪽에 누구래 저단다 디조 미트니 가르소레 나란다 오지나 다 디조 간데지 레기 나삼네 소소레 잉요야게다 뒤서직 된대저래 샤상고 다디는 디체자다 디게 겐라 넘버 솔로 도나치도 슈베 세둥원감다 지금 아주 낭베 바루를 드르죠게 뎁된데다 겐라 콘도 다이 낭에마 닝바 타오 피직스야다보다 군두인게 차듭다 디리 카셰 낭다 원감 세릭 란다 낭주 바루를 드르죠 망부진의 세릭 바랑 틴죠 단다 딘데레데 요레스 and when the chashana Tibetan Buddhism and modern physics Victor Mans for example the gengamala during the tanda azu phyik to lo ina nganzo shayam za mai ba tebran serik ba ran sedung ngam serik ba ran ge tinjo ge debde zo siktu wa ina pendo chembo yore gela during tanda nganzo loya yores phyina ta di thamadela to zo so be zo men nga kamaji okay yeah The Kamajik law, you know. Sorry, I beg to 1 minute because yeah. That deal another Namju Gunduge Sungudoa, and it's setting on come Seriki Tawa de Mama Chedu Kabri Simsam Beta to Davo Shake Duda, Sunya de Kari Resina, Tangi Gang is Sungudua, Dugan Namsha, Takje Chigitone, Dugan Namsha Dungiore, Takje Chigitone, Labgan Namsha Dungiore, that is what Andangazo Rabara Vegan. That Tuje ran all do can't read it. 단다 간저 어디에서 단도 장라 어디 배터 사야망고 데블 당겨라 어디 깐직직 당연도 장라 얌센시데 망고 당연도 양다가랑 랍 넘버 되는데 우군이 요바이나 뒤직라 우군이는 주고야도 다 딘데게 직지도 다 뒤직 ngo번일 요고 다팅 우고데 간엔 주만 주 다대성에 주제 십사부 계셔 지당 말다 셰도 딱제 제네 뒤에 간엔 주고도 왔다네 뒤에 간엔 주요면 시와 대체 칠로데라 가르된 거여서나 뒤게 넘버만도 랍게 넘버도 된 거요 말에 다 간엔 주임에 마시 받아 마데 공라 가르된 거여서나 랍랑 게 넘버도 된 거요 제가 지단 세력 버서 남시 걸 시엔도 천이 요 말에 랍버도 ngogam 세력 버서 남시 걸 전에 엽다 쳐고 이나양 단 딜레야 observer effect 지 요사르다 따오브 숙jen지 요사르다 선에 고 딱제 가제 제비나래 된 거요 봐대 되던데 잘 알레 캔서 딜라 딱제 진행되게 간다 미인 거야다 요 말에 주제 덤베나가 심죽 진행되게 비기 아는 뒤들은 로살라 가르제니 숙제 되게 그래서 디체네다 디고르라 망아 갱게 단다 겐다 겐팀 답뱅원에 전에 코나 넘버 2 이나다 베데 톨로게다 딜 카란 톨라 장바 친조 인자 티와 티툼나 빼미시 고갑레다 아란조 남주다 셴자 마임바 오네 제르바 저기 가리시게도 디 티와 티야고 고갑레 세상 디직체 다 딜레 찍라 콘소 가리시고 그래서는 다 계시 똑십 제베 가돌라 똑십 제온디 랍게 넘버디 듀네 듀게 넘버 차기 요이나 다 배차샤나 단다디 웽나슬람니 세르바 깨다신 보고 노뱅공감 세르게 자가란조 직동급자 두줄에 숨로라 공기 세와 있는 남시랑 주도 지기도 남시랑 유전을 숙전 되기도 자자자 캘린 거래 공기 공 간데 캘린 거는 배낭한저 족보지 공기 족보직당 공이 딱제 심주간라 대요와 이나 다 미치기 배치로 되어다야 콜라도나 심주간다 강가로데 단다디 뒤다 랍 녜메게 내버체 콘조 딱 간사직라 다 이게 딱제 심주간을 미치 뒤대요 미데게 딱제 심주 제바다가 tum데데 코비게 뒤 간엔 로요메 텐디 그데 뒤게 넘버 템바 하고서래 콜라야 랍디 녜메게 내버데 말에 쟁너게 내버데 그 뒤게 넘버데 타쳐서래 이나 칠로기 강사되게 뒤데 간엔 로요메데 되게 하마고도 콜라 단도 뒤다 랍게 녜메 대요로 대요도 장래 뒤다 랍세야 돼 뭐베팅라 요래 강사 소소 통화다 두게 요래서 이게 나라 된조들라 뒤다 랍 타쳐서래 강배 나라 된조게 세릭 받들 다 강배 칠로를 대네 족보되게 따용도 뒤다 랍 녜메 차들 단도야 디지도 장래야 다데 좀쇼 가시 나로라 세둥원감 세릭 시송체나 ngoborangone 두게 요사 말이다 따오베 숙전 자게 요사르다라야 계제들레고 딜레온도 단다 데 군두게 갑레도 딘데 첸다다 심잠베다 줍다 안에 데스 타녀고도 와서 송네 송야 데레 디골라망아 겐락 송그레 쉐 토체나
gish tabgila ane tuji chesi shuyi ane DJ ki ane tamshi chingin di gen ion dusham chagyo ane genla gi ane tanda chenji ki kanyo se ta di tanda ge tabgila gi ane tamshi ki jugjong rang chagyo cheza ta yugi nezu tub madu se di tawabyo ki chigyo da yo mare se ta tanda chenje manje se di ko chenjing ken ki ane khangsa yo me da di chenjing ken di su sha go re mare se di zu ki kejeli yo songzang ane chige tawabyogi shukjen yang lairela tega na shita chenji ki kanyo se di yang ane ko nangdun chikpa shigi yo songzang ane di gola ane gen iyan la kishigre ane gen iyan inbena tanda nga zu di dugi samwe ki demdun di nanglo la ane lupdi chingi ki kigen soji chadi yore ane Ian please it's your time now.
No, I just wanted to, yeah, okay. Well, I was gonna, let's see if the slideshow works. No, it doesn't. I don't know why it doesn't. No, but it's, yeah, you need to switch the displays. But that's all right. I'll just do it this way. Okay. Yeah, but that's gonna, you have to switch the displays. It's okay. I can. I could just do what Topka did. Yeah. Don't worry about it. Well, so I'm just Tashi delay. Nimingla Ian Yin. Debo Jimpe. So I promised Geshe Lakdor that I would learn a little Tibetan, so I'm trying. I want to start by thanking His Holiness the 14th Dalai Lama for his vision of creating this program. I want to thank Bobby Sager and the Sager family for funding it, and also for Geshe Lakdor for all his leadership over the years. I want to thank Bryce Johnson, who is not here, but he great leadership over the years. And of course, I want to thank what I consider now my second family, and that's Karma and Palden and Tsewang and Trinley and Tinley and Chunyi and Lobsang and all the people at the Science for Monks for being such wonderful people and feeding me so well. And of course, I want to thank my students, and I really appreciate the questions that I get. Yeah, I'll just do it this way. That's fine. I really appreciate the I love the questions that I get when I teach. So I've lost a lot of my time, so I'm going to just kind of talk quickly here. So Karma asked me to talk about the quantum measurement problem, and I'm actually quite thankful for Geshe Topka and George for introducing the topics, some of the topics that, of course, they're now completely in Tibetan, so I don't even know what I was going to say. Well, I thought Sewang was actually going to put the English next to the Tibetan. So, okay. Well, anyway, so I think my first slide was about waves and particles. So I'm supposed to talk about the quantum measurement problem, and I'm fairly certain that this was supposed to be about waves and particles. There we go. Only the first slide. Okay, that's good. So I'm going to go one back here then. So I think the first slide was actually about particles. So the second one is about what George didn't mention is that the wave nature of the wave description of stuff is related to something called the probability. So I think everybody knows what probabilities are. If you flip a coin, you have a 50% chance of it landing heads or tails, roughly. Or if you roll a die, you have a roughly 1/6 chance that it'll come up any given number. So those are probabilities. And the wave description is related to the probability that the system that you're looking at, the particles, whatever, are going to be in a particular state. They're going to have particular values associated to something that's happening. And this relationship is called the Born rule, after a guy named Max Born. And quantum systems evolve over time according to something called the Schrödinger equation. And the Schrödinger equation, the solutions to the Schrödinger equation, it's this fancy math thing, and it has these solutions, and the solutions describe a wave. So the evolution of the system in the Schrödinger picture, there is another picture that you can use to describe this called the Heisenberg picture. But in the Schrödinger picture, it assumes that the system is described as a wave, and evolution of the system occurs as a wave. And because the wave description, and the wave description, which actually this was a previous slide that I think one of the ones that was completely in Tibetan, the wave description, what it describes, because of the Born rule, we think of it as describing many possible states. So because the wave is related to this idea of probabilities, it describes many, many, many possible states. And so as the Schrödinger equation describes the evolution of the wave over time, we think of the system as being in what we call a superposition of all of these states. It's kind of like it's in all of these states at the same time, in a sense. Or that's one way you can think about it. And Tim's going to talk a little bit more about some of this stuff in the afternoon, but that's just you can kind of think of it like that. So oh, I got to do the down one, yeah. So, but what happens is eventually, of course, aside from, a few cases like George's little experiment here, when you actually look at something and make what we call a measurement in a quantum system, it's a definite result. And usually, maybe not always, but usually it tells us the system is in one particular state. So it's in one particular state. It exists as this. It's never in all these possible states when we actually look at it or measure it. And Geshe Topka talked about the observer effect. This is a little bit like that. So, and in fact, this is related to that. So we can think of the results of measurements. So when we make a measurement, we can think of it as we're in a particle-like, it's the particle-like nature. We're getting results that are particular. We're in a particular state. Whereas before, we weren't. The Schrödinger dynamics describes the evolution of the wave over time. So this is an interesting thing, because one of the issues with quantum mechanics and with most physical theories is that it doesn't tell us, the theory says nothing about what it's supposed to be applied to, right? It doesn't say, well, it's only supposed to be applied to particles. So technically there's no boundary on what we can apply it to. So this bothered some people, including Erwin Schrödinger himself, who proposed an unusual thought experiment in 1935 involving a cat in a box. And there was a cat in a box along with a container of cyanide and a hammer that was hooked up to a radioactive particle, and the radioactive particle will decay, but it's one particle and we don't know when it will decay. We cannot say for certain when it will decay. So at some point, it will decay, and it will release a hammer which will break the cyanide and kill the cat. And so Schrödinger said that, well, he thought, well, this seems kind of silly. If we take quantum mechanics as being literal and the wave function as being describing anything of any size, then before I open the box to see what's happening with the cat is both alive and dead at the same time, which seems kind of absurd. And this was sort of the crux of this idea of what we now call the measurement problem. I mean, it's a much deeper thing, and having 15 minutes, it's very hard to sort of squeeze this into 15 minutes. I'm going to add one extra little piece here that I didn't get a chance to add a slide for this, but then Geshe Topka told me he was going to mention Wigner's friend because I introduced him to the idea. So there's another experiment, a very curious one, whereas you could put Schrodinger and his cat together inside another box. And then you could be this guy named Eugene Wigner, who was another physicist, and you could ask, well, when has the measurement taken place? I don't know if the cat is alive or dead until I open the box and ask Schrodinger. And then Schrodinger can tell me, oh yeah, I opened the box, the cat's dead. Or Schrodinger could say, well, I haven't opened the box yet, so go back outside. And so there's this question, and this was related to whether Wigner was trying to sort of get at whether consciousness collapses the wave function, but there are some deeper issues here that Geshe Topka had talked about. In any case, this measurement problem goes back to it raises some interesting issue, and there's a very, very famous physicist named John Bell, who he made two comments which I thought were interesting. The first is that this concept of measurement becomes so fuzzy when we think about it, that it's really surprising that it even bothers to, like the fact that it appears in a physical theory at the fundamental level seems odd. Like, why would it be there? It doesn't make any sense that it would be there. And in another quote, he said, conventional formulations of quantum theory, and he also said quantum field theory, are unprofessionally vague and ambiguous, which is a curious thing to say. And I dare say that I agree with him on this point to a certain extent. One of the things that quantum physics is very good at is making mathematical predictions about what will happen in a laboratory. It is one of the most accurate theories to be developed. We can predict to several decimal places how certain things will behave. On the other hand, we have very concrete things that we see in laboratories, and the math connects to the experiments very well. What we can't seem to agree on is how to interpret that and how to talk about that. And a lot of this comes down to the measurement problem. And so what we're doing is trying to explain this idea. So to put it another way, the Schrodinger equation describes quantum processes, right? So this is the one way you can describe how a system evolves. Again, I said there is another way, but this is the one way we can talk about it. Measurement itself is a process, but it's not described by the Schrodinger equation. It's not in the Schrodinger equation. There is nothing in there that says anything about measurement. So, as John Bell said, why would any good physical theory have two different descriptions of processes? We have the Schrodinger dynamics, which explains how things evolve and the dynamics, we call them dynamics, how things change over time. But then we have this description of measurement, and this is a process, but it's a completely different thing. And why do we have it? And that is sort of the crux of the measurement problem. So most interpretations of quantum theory are sort of attempting to explain the measurement problem. They're attempting to work out why are measurements not described, say, like we have the Schrodinger dynamics, but they don't describe measurements. They describe processes, but they don't describe the measurement process, which is a process. And this measurement process seems to, we have this problem of it doesn't tell us what size it applies to. Where does quantum theory, what size does quantum theory apply to? Does it apply only to the small things? And these are all sort of issues that we're trying to work out with our development of interpretations of quantum mechanics. So we're way past tea time. I'm gonna close with one other thing that I really wanted to get at, and this is going back to what was talked about yesterday. Why do we care? Why do we care about this? Who cares? Is it going to help ease human suffering? Well, here's my answer to that. One of the things that makes us human is that we wonder, we question. When I was a child, I couldn't stop asking why. Why? And I still can't stop asking why. It's fundamental to who we are as human beings to try to understand the world around us. So, yes, there are plenty of practical things that come out of quantum mechanics. Quantum mechanics ultimately, not that you would ever do this, but it ultimately explains most of chemistry. It's fundamental to it explains transistors and semiconductors and things. But putting all of that aside, why do I care about this? Because I want to know how the world works. I'm a human being, and it's what makes me what I am. And I think it's what makes us what we are. So why should we care about this? We should care about this because we're human beings. It makes us human. It distinguishes us from other beings. We want to understand why the world works. And I think that's really important, and it gets lost sometimes. And I don't want it to get lost. So, Dr. Shea.
So you managed to finish in 14 minutes. So you gave 1 minute to Tapke, so that's good. Laso ane gela number lenji zu tsangma ane tuji che shya da damshi chinga tsangma tuji che shya yin dine nganzu da soje parsing di ane chu kamani shu tsapshi chai do ni sum chu songa shipshenga la kamu chu chi nyur dang kesar ya gela nganzu tuzu mangbushi tanjin gozu ma to nen laswa ane tea break until 10:45. So we are reducing or stealing 10 minutes from tea break also, not only from the
Don't look at me.
presenter's time.
Wasn't me.
Okay, yeah. Thank you, Tujana.
Thank you. Yeah, that was
and its explanatory power and what science actually aspires to do, explains the world which we live in. The other connection determinism has with, it's with human free action. Even though I'm a philosopher, I will not talk about it, but it is connected also with the Buddhist concept of karma. The problem of free will and determinism is the problem you deal with when you think about the concept of karma. We will leave that aside. We can talk about that during the discussion if you're interested and so on. Let's just focus just how determinism was fundamental or central in shaping our understanding of natural phenomena. In order to describe the world in deterministic terms, we first have to be able to actually completely well define the state of the universe at some time, a description of everything what exists, and also that we have the kind of physical laws that are exceptionless. That means they are always universally valid, and determine exactly true at all time in all places. And they fixed exactly what's going to happen in the future. Well, all the time I am talking about the future, but it's not just the predicting the future. It's also, if we have deterministic laws, we can predict both future and retrodict to the past. So any fundamental theory which we are familiar with, which we know as a deterministic theory, it's time symmetrical. That means can explain, can predict what's going to happen in the future, but can retroactively also figure out what happened in the past. So, for example, we can predict when the Halley's Comet is going to come next time, but we can also retroactively figure out when was last time in our sky. This is what we call determinism. Theories that can do that, that have that kind of laws, we call deterministic theory. The good description or insight what determinism is, the first time was offered in the 18th centuries by Ruđer Bošković. 50 years later was repeated by Laplace with so-called Laplacian demon, but it exactly says it's called Laplacian demon because it talks about the creature that has enough cognitive power and enough knowledge about the state of universe at some point and all the laws. That kind of creature could predict that we're going to sit today or at this point, right now, who's going to be here, what's going to happen. That creature also could figure out what happened 50 years ago. Also knows who was how this program came about, everything. That's the reason it was called Laplacian demon. But it's here in this description, determinism, which comes from Ruđer Bošković, you exactly see that. Give me the laws of nature, give me the position, velocity, and directions of all particles, and I'm going to predict, if I have enough cognitive power, I'm going to predict everything what's going to happen. This is what determinism really is. So now our main question is, do we live in the deterministic world? To answer that question, we have to look what laws our best contemporary theorists postulate. Are those laws such that they can do what I described, that they can fix exactly what is going to happen in the future and the past together with distribution of matter? You're all familiar, you probably heard about Newtonian classical physics, Newtonian mechanics. In Newtonian mechanics, it's taken completely to be deterministic theory, because according to Newton's laws of motion, together with the velocities and positions of all particles in the universe, I'm gonna calculate future and past states with absolute precision. Theory of relativity, the next well-formulated theory. Of course, there is a special theory of relativity and general theory of relativity. Special theory of relativity is more easier taken to be deterministic, but even general theory of relativity, if you take it, that is models the physical universe using different spacetimes that satisfy Einstein's gravitational field equations, could be considered deterministic theory. And then something weird happened in science. At the beginning of 20th century, quantum mechanics. Quantum mechanics is a very different theory than any theory which we had up to this point. Why? Because it's for the first time we thought that we have a non-deterministic theory of the world. Theory does not predict what occurs in specific case. Rather, theory tells us just what are the probabilities for different outcomes. So these are very different laws that we were talking up to now. When we think about decay of radium atom, we actually cannot predict with absolute certainty when the decay is going to happen. If you have a chunk of radon, you don't know when particular atom of radon is going to decay. We can just have probabilities when this is going to happen. That's the reason when Ian was talking about the measurement problem and Schrodinger's cat, you saw this example that the vial of poison, when it's going to be broken, depends on that decay, depends on this random process, when it's going to occur. So in quantum mechanics, even if we have a complete knowledge of systems wave function, now you know what the wave function is because you heard from Ian. Wave function really is a mathematical object. But wave function describes a quantum state, complete quantum state of the universe at some point. Even if I have complete knowledge of systems wave function, I can only predict with certain likelihood what is going to be outcome of some experiments. I could never know anything with absolute certainty. Randomness, for the first time, challenged our traditional classical picture of the universe that is entirely deterministic. That wave function, evolution of that wave function is described by so-called Schrodinger's equation. Of course, it's called Schrodinger's equation because the father of the equation is Schrodinger. That equation is completely deterministic. But even though the equation is deterministic, it actually describes evolution of the system just in a linear superposition of different states, of different states. So when the cat is in the box, before anyone looked, observed, measured, before anyone opened the box, if we have only wave function, that cat is in the superposition between being alive and dead. We know we never observe the world in superposition. Our world, which we observe, is always in a definite state. Thus, something is wrong here. Einstein noticed that immediately, and so on. So the problem, this is what we call the measurement problem. Philosophers, at least, always used to call this measurement problem. And that measurement problem is how to get from this wave functions, physical theory. We have a superposition of different sides of this problem in front of me. So one possible solution, which sort of was provided at the beginning, mentioned several times here, that during the measurement and observation, what is the indeterministic. And know in which of these possible outcomes, these probabilities are determined by Born's rule already, which Ian mentioned, and also based on system's wave function. So now when you know what is on the fundamental level in quantum mechanics, you have to ask yourself, is that the world we live in? Is it really now? We got the answer. Our world is not deterministic, our world is indeterministic. Well, that would be too fast of a conclusion. It's gonna depend on how you interpret quantum formalism. As is mentioned, we don't know still what that theory tells us, what is on the fundamental level, how these things all work together. So that's the reason we got in the quantum theory these different interpretations, which are really different quantum theories. And depending on these interpretations, we're gonna say, well, anyone who thinks about fundamental problems would not take it any seriously, despite what Topke said, namely that what causes collapse of the wave function is somehow my observation, conscious mind, which immediately you think it raises a problem. What happened with the world before there were any conscious minds? Or what Einstein would say, who's going to collapse wave function? Do you have to have a consciousness of PhD students in physics, or mouse can equally collapse wave function? So this Copenhagen interpretation is indeterministic interpretation of quantum mechanics. It's not really good physical description. There is another theory which is equally has non-determinism, out with a much more acceptable physical description of collapses of wave function. When do collapses occur? Randomly. For no reason whatsoever. They just happen. Because of that, it's a much better description of what is going on. But in its core is a complete indeterminism. Then, apart from this, collapse theories, Everett's theories, that's the reason there's a picture of Everett. In Everett's theory, wave function doesn't collapse, right? We said we need a wave function collapse in order to get the definite outcome. Well, world splits. There is one world in which there is me and life. So this is a many worlds in this, doesn't have any randomness. So we can say that then we have something which should be familiar, but he says he was his first science teacher. Dilemmas, do we deal with the waves or do we deal with particles? Bohm says we always have definite positions, and mental theory, the future positions of particles and velocities will be based on wave function of the system and particles, this initial position and velocities, which particles really have. So that theory is fully deterministic theory of quantum mechanics. So what we saw right to this point, that quantum mechanics is open to both, the quantum formalism is compatible with both explanations at this point, because we theory of the world we live in. Good. So now, just at the end, we already talked of the most important experiment in quantum mechanics, at least Feynman said that, is the double slit experiment. In double slit experiment, which was already mentioned here a few times, you had a beam of particles. It could be photons, but it could be electrons, it could be larger particles, is sent through two slits, through openings, and there is should pattern in life. What George was talking about today. So, beyond barriers, that already described, that is the textual screen that records where the particles arrive. So now we can have a what happens in classical case? What happens in classical case, if I fire tiny particles to some slits, what's going to have like a paintballs? Each is going to go through each slit, and we're just going to get on the screen behind each through the door. If I open one door, right, I'm going to get a band of where these particles, where these paintballs landed on the detector screen. If I open another door, I'm going to get another band where these particles end on the screen. The question is, what happens when I open both doors? Well, you would think you're going to just get those two bands where particles went through the door, or paintballs went through the door. To describe that, when this spreading causes their interference, that interference, what that means, if crest of the waves meets the crest, they're going to be amplified. So this is constructive interference. Where crest meets a trough, they're going to cancel each other. So now this is going to call the destructive interference. This is where you get this dark thing on the screen. I already showed you. Quantum case. I shoot particles through the two slit, and what happens? Each particle, in some sense, right? You would expect if it's just particle, it's going to go through the slit, and that's the end of the story. We're going to detect it just as in the case of paintballs. But what happens is we end up again with the interference pattern. It seems like each particle going once when you fire lots of particles like that, you're going to get your standard interference pattern, right? First from individual spots on the screen, but more particles you shoot through the screens, you get this interference pattern. This very important experiment could be described deterministically. What pattern you're going to get depends on the description, very precise initial description of the system. But it can also be described indeterministically, that spot can form in different places despite you having the initial condition described. The same initial condition could end up result in the particle being in different places. So, before I say thank you, the conclusion is, at this point, we do not know whether we live in deterministic or indeterministic world because we don't have a finite theory of the world we live in. And just a comment like everybody else, why do you guys, in your Buddhist studies, now on top of Buddhist studies, you should study science? First of all, science, but of
gen Vishna la pujiche shuyada ta dijela ngazo nyamshu thumu ki ane khogap di duschiche ane gozugi chedan tringi jushi di ko chedung gamrik basya da tindri ki jushi dis khothabu yowada tadub da dewa yobe ki nesu mangbuchi legi yobe ki kyumzen tene ane ngazo gyuriya di nema ngazo namgu alternative chigjil chig gyuriya ma to ane tanda radio gi june da thegar gyuriya di ane duschiche chime di masonza ane gela number lenje so ane thiwa kuya khokap nyungwa rairwa cheza dila jo sambal thiwa yakbo dinde guro chi ma to choshida mi ge de ma guro ches.
Thank you.
Lana
te dan te du gi chan du la lab la chi so na gdo te du thanche la lo mar sang gdo du le de lo yo ba de du ti chur ro du ko yam cha du la ba long du te gi ko lo ti ni de ne dan te te jo ra nga cho chi gi chan yin chi gwe chi dar la na nga zi na ba sang je ba de ba ma nga Shadang la soba teso chebe mangawa cheba ina yang dusha ki tono chama xia momo legire o tendi ki tono pegi ndonga jesa jidwa kesi ndonga meba ina jeko yajen roya yomar matang yajen roya mar soso ki shiche yajen roya yomar ndonga pesho tanya jora yu tela tsenze ji gogore sangido te reda mare o teki tono kalin ji zoro na shui.
Yes, then it is more lighter kind of elements or
Nature to it. I would actually phrase it as there's nature to it. I would actually phrase it as there's a system, there's a physical thing. As true experiments, we have found no limit. Scientists, even beyond atoms, molecules, even maybe beyond molecules into larger.
sujing ngo por chika jigo chungwa yamana cha den zo ting la yö ding ane rakba jigo che den zo ting la me ding den ge keje mares tsenri keje sha jing ngo po thamche la yö be yamana dunjeng ge ru yo wa de ane ke le la ru yo res che ta thanda yim be na nga zo dunjeng ge keje je da yo ane nga zo ge sha mares.
It's so George is right. We applies to. It's a theory, and we don't know where it stops. There are scientists, good scientists, who believe that you can't you can't describe the universe with a wave function. They think it's an absurd concept. They think it's absurd to be able to describe cats with a wave function. I think, and so the reason I wanted to point this out is because there's this I think people think sometimes that it is up to a point. One of the things that keeps me employed is the fact that we don't know everything, right? And one of the unanswered questions is this, and there are some scientists who have one opinion, and there are some scientists who have another opinion, and hopefully some time down the line, we won't be able to settle. But I just want to make sure that
저다 델라 찍는베 야고 삼송 세딩공감 릭베 나로라 아니 내주 망보 시도와 뭐베 내루던 대와 요베 내루던 대와 요베 내주 망보 시게 되니 베나 내루 데르다 세체 타초 키 산삼레다와 찍게제 시마레스 싱겐데 요레스 저다 델라도 삼발라 세딩공감 릭 콘드시 약방 체도라 소샤와 제레 마루와 체수수긴 퇴모메이 베케 아니 데시
소다 게겐다 게투 티 잉에 저데 다단다 체동이 건을 바래 티 인도 티 나로래야 당아 추기 하래야 당아 추기 하장 그 개첨부 쇼비시 지와 니시도 봐라 네 하고 장 그 개첨부 쇼비시 지와 니시도 봐라 네 하고비 아 근데 판다미터 파티클 티시고 봐 라이트 제장아 주미게 롱통통고 말아 제자 티 인도 롱드당 아 단다 외두니래 빼는 수 롱된 쇼비시 된가 첨부 라바르당 수 낭추고 나로래야 hardware the software個嗰些錢 hardware the software個嗰些錢誒你啱做專門通的個吧接着啲個單啲嘅誒你啱做專門通的個吧接着啲個單啲嘅對 interdependent 差的個對但係因為對但係龍咩比呢 single 個幾個嘛對吧啱做農區個農路誒米了別下個對吧剛把咩比米的個
제가 손대길라
啲嘅但係主要的對吧但係nen가 첨부를 다主要的當波嘅啲嘅가르사 세우 쇼지 매바이나 렌테 토마르와 제자 티인데 다단당게 가르쇼 워르세들라 에 로와다 롱기 룬들 당고 에들기게 롱기 외도 가르치는 까 토요 마레스 로와 룬도기 외도 가르치는 까 토요 마레스 티인데 외도 송소로발라 단다 오마데 티 아니 조바 요 마레스 야지 타게 나주 텐스 돌타파 샤고르와 제자 대당 아니 yes last two.
Okay, so two questions, okay? For the question, first question is, so when we talk about the particle physics, so I think that there are two most important particles. One is the photon and one is the air molecule. So if we understand air molecule, that's what I'm saying. When I say I'm in his place of mind and without or interfere the travel open to everybody, and the size to be there since the beginning of the universe, at least. So even though we cannot say that protons are permanent, non-changing ever, but for a very long period of time, it can almost stay like.
Check.
Yep.
Last night, I went up to the roof of my hotel, and I met actually Professor Chris Impey there. It was about 6:30, and we looked to the west, and it was a clear night, and what did we see? We saw a spectacular sunset. And we marveled at the sunset. And I invited you to dinner, but you were busy, so I went off to have dinner afterwards. And what does the sunset look like? It's quite red. And then another part of the sky is blue. That is exactly what you're saying. It's air changing the path of light. Depending on the color of the light, it's affected by the air. The magazines that go to the moon, use to Mars. And he said, well, George, the strangest lows. And sometimes we don't know it. But in situations such as the moon, where there's no air, they find it.
gelagi tiwa thangbo jorwa di nobcho ke namka di khado maure de shas di khachini cheware sidu zambala ane wedul sigune re we droya dila lungki duki shubjen cheba am timit the one who went Harrison say yores chesa khona ane dawe ki tenglan tongking ki mi ki nanglo nyam to kuma sa mingmar da chik dinde galan droya yimbena ane di kapsule ende ji surgi re samya ki ta ko samlo khorya ki chetula kerang ki keje kharshya yule sambala khorang ki khallas lavi mena ken sa shu di 아니 ngaru nyering kin dushi lol shartan jorwa dipet manda ware shas dawe ki tingla dus te du zambala damla yowa do chimbe na ko pet tharing bu shiu yimba thongu dus la sons ta di khachin chigi yore se du zambala ane dawe ki tingki ane lungkham kin rotan de da ngazu zambuling ki ting lungkham kin rotan di loga yimbe kyomsel tene ane we la khacho gyurtan da we la tangzi chetan da manda windu ane loga chawan thongu yore ngazu zambuling ki nanglo la ane lung ke we la ke chigi mesar sam goya di chitan lungkham kin rotan rahodo yewe gyomsel tene chebar thongu yo shiran thongu me wares cheta da dawa da dene ting yimbe na ane se thongu yores kirang ki di
지당 견라 콘서트나 야에 네 단계 지당 등 간주 답변나 뒤 참모대도 갑갑을 간주 메다고 제시자야 펜도 요레스 뭐 대도 나란주 대동에 갱코랑라 계자 양자시티고 있나 it's like without interaction seems to be no decay even decay is very long so argument is here is that in Buddhist permanence everything is impermanent at the momentarily change and then
There is a free proton, which has theoretically the half-life that's longer than the age of the universe. Now, if I had a room full of protons, so how have trillions of protons? Just enough. The statistics allow us to predict the half-life. And the half-life might be the age of the universe. Now, we don't actually need to see many things decay in a short time. It just means that if I have a kilogram of it, then after a million years, I'll have inside a nucleus. They actually decay all the weak and strong nuclear interaction.
The gelangi tandat podudi bembena ya week nanglola ane decay se da se romando se sengur se tanyeng yemang zo pyur chigiwa chaza da se mase ki keja shedu sambala zo selu se tani keja shegu yores selu se tan chik tandang ju girik den zu keja se ka she tang zo jigden kham ki ane tandeng ki zo jigden kham disi yordan jigden kham di ki ane ta chesel ringwa den de ki keja shigi yodu sambala ane di ko che ki thuyule den de ane rangwan chen ki ane podu thangka di ane pad ya mangbo shiuji हाँ साया के चले के मंगबो शोबे बना अने दीग नंगलो ने अने खंगरुंग चिकी अने ठंगा मंगबो के वसना मारे सिगियोर त दुनथें के नंगलो येबे के तंदा तेदु के नंगलो येबे पोदु दीना अने नामशा गुंदे ने को सेंगुर डोंडो बरेस कोन सेंगुर दुगी अने पोदु दंजो अने मनिंग के दुग ngो सिगियो so न्यूटन से दीग दुग ngोला अने पांजुर के छेदु योरे से वरता okay Chris and then Wanda Chris and then yeah Okay, dijela chola soinda kasani tangmungene gyabla yoache nine ene lawa chanya nyu mbosonza khuzul ko kapuinda.
So I have a short question for Vishnu. So it seems like to go beyond Copenhagen and wrestle determinacy from quantum mechanics, you pay a heavy conceptual price. You either proliferate parallel universes with many worlds, choices in those scenarios.
I think at this point quantum. Copenhagen interpretations is not a description of when collapses. And on the other hand, you don't know what probabilities mean in that, because how can you have probabilities in the world where everything is realized, right? What does it mean? Cat is 50% dead or alive. They're alive. There is a world it's alive. Everything is realized, right? So there is a world it's alive. Everything is realized, right? So Copenhagen is out anyway. We are trying very hard. And there are waves. We're not wedded to any particular theory. We are trying just to figure out which of these different theories that are offered to us really give a close to physical, but I think Copenhagen is just.
Ene ngol yoresia ta di desh sodo da digananshi ane labge chele shikba se ki ane nezu sawa de ane labge chele shikba se ki ane nezu sawa de mangbo chi gya gu yo sonza di ene ko tonda mesala sosu kangete de di ene ko tonda mesala sosu kangete de wa do chimende wes 아니 모랑게 칼라기 요르세도 삼발라 대가랑 레스 제가 제가 아니 다 대금스틱 아니 다 대금스틱 아니 다 대본 동금에스 제가 아니 우연히 수치 대본 동금에스 제가 아니 우연히 수치에 임베나 아니 직답 임베나 아니 직답 대외고 토네 아니 랍가 정신데 여데 남 대외고 토네 아니 랍가 정신데 여데 남샤 레라우딘데 요레스페 와 남샤 레라우딘데 요레스페 와 남샤 시기와 줄링게 마레스 남샤 망부 여웨 남샤 시기와 줄링게 마레스 남샤 망부 여웨 낭로네 따드르그 삼로 당당 토낭로네 따드르그 삼로 당당 토네 가레 테사레다 마 테사 마레스야 디게제 신도 삼발라 보문기 데시 약단도 빼답데오 아니 레라오 약보든데 아니 통구도 산단도 빼답데오 아니 레라오 약보든데 아니 통구도사 okay then wandala and then I will go to the
망게서래 다나 조자바 참만한 소리도 제네 내가 다나 태가를 체등이 공 경우sol다 미세 저 미세 탄데 샤메로와 마이나다 실지도 그 과거네 니도 급하다 시리사주 참만을 짜이 디디 체등이 공 개개 몸벌 가서 저바를 용대 그러와 디지다 콘솔 내가 간디지 자기 메다 갈아가서 쳐보태거든 디지 링게 단다 게시 tanke 라서 게시 tanke라라 저바이로와 진짜 가르르잖아 다다나데 가서 캐모캐서 뭐 패되리 봐 참에 그 동시 시비 난게 요래 세등인 코데 가서 나지 오세도 시비 다 탄로야 봐 순대 걸어 봐 다다리 게시 tanke 오늘 지가 첨보래 비무시 야보 요래 봐 디지등에 게시라 태가를 줘 봐시 다다나 가서 소징인 코데 니보마베 따도 통본도 와데 나봐서 챘데 그러 봐 그때에 다다나 가서 세등인 코데 아니 무슨 그 배는 제글로 니수제데 들라메스 봐 참에 그 던체 참모 시시가 요래데 차님의 그 던체 참모디 그 라시데 이 자원이네 매den게 그러와 이 자원이네 매den게 너무 많이게 덤비랑술은 대den게 도시에도 잠발은 저러면 코로고 있다 디나로를 돈이 요러와 근데 이나를 수치는 대는 것도 돈이 제대로 될 거로 내자 요러와 다 저러면 이보면 그 전타데 다 세딩이 것도 많다 봐지 그 맞아마 예와 제저러 어세 다들 던게 예나 어세 그 유용가 나로라 더참에 라시데 템베 제요디 체드니네 셔러마발 가르 드드세나 더 참모디 인지미지 덤비랑스도 내가 그랬어 다데 로스 센스 비주도 슈치 몰래도 와 다데제디 아니 더 참모그 라시데 덤비랑스 고 던체그 라시 녜바데 그리스 드얀데 소징이 거 다더래도 와 세등이 거 누나 땅 예매 라시디 시인도 라지 라시 시인도 좀 더지 라시디 시고요 말아 데제디 땅에 저박하도 되라다 세등이 거데 우세도 터세게 야나 우세그 유가 나로라 더 참에 라시 템베 제요디 녜바도 더 라시 고 덤비 라시데 녜바도 그르스 슈치 뭐 드데 치다 아니 제도 되게 녜메 유가 나로라 때 금마레스 봐 던체가 라시는 대대와 주지 라시는 대바르스 저기도 디지디 다 기실라로 디토라 고스 칸데 얘네데 세워주스로 치스 와도시
저지랑 어제 세워라고 쳤으네
저와도 노지다 세등이 거데 나지지는 간수 아니 시도 더 참이 그 참여 그 더그 라시 템베 제요디 니준제데 더라메스인데 더 참이 그 라시데 그게 덤비 라수는 세그 용가 나로라 동베 라수는 지금 말했어 저도 동반이도 들어왔다 동반이 끼지 들어가라 봐 대체도 코니 단다 뒤에 쳐서 셰데 그 동반이 말했어 그 이지메지 덤비 라수를 그걸 해서 추지 못 들어도 와 원다데 드얀데 아니 세등인 거도 딱 간지지는 통보차기 어려운 것 같았어요 좋아요
뒤처럼라 이비메 될라고
다 저거 되려
식당기 딱nga 단다 서버랑 정마서 니송 주디 둘라메세데 너데베기 페지 단다디 되바 예삼데요 가인스나 너데베 입디 딱베 소리지 간제 데멘두제 소리지 숙제 멤베 소리지 저랑데 도단 제비나 입디 똑다 진짜 페지 직 입샤 미투베 소리지 양나 샤비나 똑다 샤고베 소리지 제 다디 찌기 용사데인다 니송 주디 둘라데종 안주 둘라 입요레 요마레세데 뒤차랍라야 듬베 입요바 송바데 심자메 숑카직라 요바체 뒤차란 듬보 인고 바티체 첼라 이메 디기 차네 코스 pena marita dotibe tayon du yibde oh ya 어디도 다 제바면도 다 간데 링아조 베데 다 가서를 철어난 게 저바베 십자고든데 지 차드샤 데 내가면도 당에 계제데 베지 반부체네마 슈긴이 땡아조 지당 아주 단다 제등원감 데 당보 미팅바 베지 슈바이나 니망아 게레도 tumbutum불레 콘저 갑직랑 알 딘데스기도 tumbutum부 셰단데 지난주 기대저 다 대저 대셰자도 무트니 용야 딜레 tumbutum부 내야 공이 타세야죠 와 세두세 디니 tum바면도에스 아니 딘데스제네 양코 도전에 저베 잡초도 강다리양 딱 내기 좀딱내 갱게 될래 저와대배 칼소 빼제 띵나고 제는 갱 지장에 차상지 렌테마서 이나양 지용게 렌데 가르자고서는 넘버 탐제도 툼바데 자원에 말해스 제도 공감 세력이 간저게 유쟁기 내 당기 수주제샤 유쟁기 제발에 세야 될라야 건조 단다디 유쟁로 섭다 뒤로 유백까지 되다 로이 딱당기 차네 제세지도 장래야 똑바에 따세야 되다 건조기 유쟁기 숙쟁 세야 되게 람산 직발레다 매와되다 세버레셔 저단다 돔데지 쉬와이나 단다 게랑게 트와되게 태게 랜딩에 슈트마서 지용게 랜직다 고 탐제 대대we 인자 동매직 쉬와이 다가랑.
So just briefly to translate the discussion, the questions was when we talk about these fundamental particles or the partless particles in the Buddhist traditions, the Vibhashika and lower schools, they talk about the formless nature of these fundamental particles. They don't have a particular shape or form. And then the higher schools like Madhyamika, that is associated with fundamental particles. So if that is the case, then normally when we talk about the quantum mechanics or the quantum physics, people say that quantum physics is more kind of in tune with higher schools like the Madhyamika and mind-only school. So what is happening here? So Geshe-la is like overlap quantum physics with Madhyamika or the mind-only school. There are some angle in tune with Vibhashika or the lower Buddhist schools. Even in our concepts like this measurement problem, where the measurement or the observer is doing something onto the objective particles. We are actually in quantum mechanics or quantum physics, we are talking about changing the nature or the results of that objective reality. But in Buddhist schools, in like Madhyamika, we're talking about our perception level, how we perceive them, and not much about what our mental projection is doing onto the objective reality. So that's what was the discussion. Yeah, Tsumatsu, the Gabla.
So thank you very much for your presentations today. I personally am very interested in quantum mechanics, so it was really a pleasure to be able to hear different perspectives from science and Buddhism as well as philosophy as well. So my question was about quantum entanglement. So I'm quite interested to hear about your perspective on how quantum entanglement works. And from your perspective, why do you think it works in that way? How can one particle in one place explain quantum entanglement at this stage?
Cholagi Tiwadi and Sidur Zintil Laj, your entanglement say, the Digola Red Doa. Chaza Digi Tiwadiki Chetula, Ningun Gabkin Soden, Gan Timki, and a Takamachonga Ringala Cholaki Tiwadela Langang race, the Imbasonza and a Consequentia Moa Chesa. Next question, please. Answer to the nuns.
Space like the Tongcha Ruchi. Tishidigala Namka di the space land to the Tongjet. The Mevachai, the Mevor, the Namka Mevachalabut. The Yorio Maris. Kissing Namka the Mevachai Yovaina, Namka the Meve Nekapla, Nidugi, Nepopti. Contest the Namka Tongjatian, Ni Korean Dula Deni, Shagiore, Du Mena, and Tongja the Shatu Yorio Maris. 저기 아니 이것도 비슷히 심이 딱지치 심이디 시어를 요 말세줘라 디 딱지 칭이디 딱지 칭을 알리레스 와 딱지 칭이기 딱지 마치 봐도 심이디 시어 줍다 마 줍세디 아니 가정갑 중갑주로서 찬염레스 와 시여스기를 메시기레스 대나 딱지 지도갈 그 시샤스라 그러 제도갈다 그 딱지 칭에디 율레 라테네 샤베소르 텐데디 아니 다 그 딱지 집에 자와요 여러분 자와데 다 상마 수 dom제 아니 심이디 시샤스는 다 타쳐와 디바도 심이 시와 랍도고 말와 메디발다
Okay, so first question. Okay, so first question is for Geshe Tapke. In science, when we talk about particle and space, we need space for the particles to abide. Space is permanent or not. Whether there is a time when there's no space and there's particle. If is it possible to have a time when there's no space and there's particle, and if yes, then how? So if before you look at the cat and the probable and the cat happens to be dead at the moment time at that time, can we say that that observer killed the cat?
두오페 야고도 다 남가다 와레고 동사 매베 뒤자요 말에서 소리지 차기요라 나이나 갱 뒤와 된간조 단다 당기 인간조 남게 뒤세야 될 디 남게 뒤세야 될 군뒤능이만에 배추 통나난디 망보 체력 발라 송낭기도 자자 디 간조 더나 최고야 제인 사례 삼구도 더 중국의 중나라 단다 배나 남게 뒤세야 될라야 대세 자당라 배나 다정로 저에 두고 대와 요래 개두제기 중국 직전 요래 안에 군제 따라 나다기 뜻 나로라 따위나 네마 동연도 뒤차장 사추 멜롱 디네 팀제 딜레 타웬 중앙직라 마 팀제 마음바나 직된 사바 차연도 양고 뒤진뉴 뉴바소리 제대 딩랍기 생리게 자다디 토나 제고야지 두 인지 뒤뒤데 자단다 디 남가디 셰비나 간조 공바저 나라 부가 남가 세야데 ngobonaला 제게와 간조 감게 나로래야 부가 남가 세야데 난다 문바 다인 로 세야게 단다 로레야 아니 문베 뒤세야 셰도와 the Serik Nalola Tanging Das Devata, Dark matter, the dark energy seate, Lagiore, Yena Conso dark seate, Nakbore seat, and Data Mare, Conso Carson, Mishibe, Kensaji Yobate, Mishiba in the Nega Mingdane, and Nabo seat and the Tanyeta, do Nabo seat and the Tahamoya, do it in the Yoba. Chazang Dizotola Tango Tende, Shimju Cheque, Mango do something at Sirin Buchak, Tanda Ding, Shimitigan 60 Shuchoji. 시미디 나에 다다 자자자 고쳐입니다. 이내 나란 삼적 전에 슈랭가기 콘솔라야 개디 대따르나 콘솔 가르쳐 버려서는 뒤직디 딱제 심주칸나라 천제 마체 공라 랍다 뒤니게 랑신라 내요레 세겨와 아니 슈랭가기 대따나 딘데기 다 내가 녜메지 요하나 딘데 시미지 요하나 지시와다 선바니가 레베스 다 디치고레마도 딱제 제니비게 딱제 가나라 단다 경원체리나 시제 시미지로 데 가상직 시와다 근데 계자다 잔이 세계 유사 말에 당한조 인지게라이나 hypothetical situations 개데 대다나 안에 딘데 인고도 시미디 시와다 선바니가 뒤타무직 랍다 뒤니가게 란신 녜메 단다디 슈퍼포지션 해야 돼 네디요나 데 시미지게 딘데 인고 마시다 갱콘서 다디 응에디 가르사 저고 제베서를 쳐서 공개해
Okay. So, yeah, you want to translate.
Space particle. So this is according to the Kala Chakra tradition in Buddhist Tantrayana. Space particle is a concept that is associated with Kala Chakra. And then when doing my presentation, I talk about this space particle. So this is also something that we need to think about, because when in Buddhist tradition, and according there are, even in Kala Chakra there are some different versions of it, or the different commentaries of it, and also His Holiness very subtle kind of like an element in which the four elements, the elements of the universe, the physical universe, can dissolve into when the universe ends, and also when the next universe happens, it is also the element from which the four corrosive elements like fire, earth, and these things can emerge out of. So these things I'm not making. So in my presentation, there, I talk about in Buddhist tradition what we call the dark science. When we talk about dark matter, it's not talking about phenomena is not observable to us. And so because of that, we call it drug, and we don't know what dark matter is. Basically what I'm saying is that there are many things that we can speculate and think about.
Can I say something about Schrodinger's cat really quickly?
Yeah. Schrödinger cat. He also said few things. I will combine both of them and then
Okay.
translate.
So regarding Schrodinger's cat, I think that's a great question. Did Schrodinger actually kill the cat? And this is something that actually puzzled as collapsing the wave function. That's one way you can think about it, as collapsing the wave function. The question, of course, is when does the wave function collapse? Does it collapse as soon as Schrodinger opens the box? Does it collapse when Schrodinger's eyes see the cat as alive or dead? Meaning when the photons that are bouncing off the cat reach his retina? And this was kind of why Wigner came up with his idea of Wigner's friend, which is he said, if you imagine Schrodinger and his cat side, and then he opened in Vishnu's, and Wigner comes in, and Schrodinger tells Wigner then when.
Again, Ian Koraningaki, any Shimidan Jeviki, land so Domche, any Jurgindarwa. Chazada Dindiki Tiwadi, that Tamugan Tabila Karsum Reslavimena, and Shimidi Musunganzu and the King Taje Khan Lola to Kiche, and Eco Shiva de Mashire, Sia di Lagio Mares. The Kachin Lagio Sedu Sambala, or some look at Tache Tony, Tanda Lab the Duke, Nedan Ding to Temati Capsula, and Labgichile Shigmashi, Di Kadu Hakumewa di, and Co Koransu Namjurtan Tanda, Chawachitan, Denzola Teyu do Sambala, and Co Koransu Namjurtan Tanda, Chawachitan, Denzola Teyu do Sambala, and Co Labganzuki Tachek Nanglola, Tes Havik Jela, Yamena Obu Ragbik Namjurtan Savik Jela, and Ninga Yindin Kinchi Medu Sambala, Ninga Yinkene, Menkenchi Lama Candes Chagiore. Kaduchare Maris Kejashi Nuzamewan Nangshin Lama Candes Chagiore, Kaduchare Maris Kejashi Nuzamewan Nangshin, Teganangshi, and a Shixia di Schrodinger, the Schrodinger Tokpo, and a Shixia di Schrodinger, the Schrodinger Tokpo, and a Wigner Koran, the Wignachu Junkin di, and a Schrodinger Indu Zambala, the Kogun will tell me, Shimise Masikeja Shevimana, Senken di, and a young Susu Chadero, Wigner Koran Chadero. Wigner Koran Gesere, the Schrodinger Gesere. Yan Schrodinger let do Gesere. Yan Schrodinger let do Schrodinger Gesere, Koran Koran Shid Yorsia, the Zuke Kandama, the Schrodinger Gesere, Koran Koran Shid Yorsia, the Zuke Kandama, the Caris Lavimbena, Lab the Deuce at the Chadu Yoris.
Yamanda the Consular and Anzo Tangulu Didua. Kongingema Samlota the Chrono Karech Tanya, Chronon Siduzanlea, that Namgate do the two. Tangazu Karisana do call Sedu Mango Chera. 다 뒤에 페이지 tumbu chen tumjo리샤 직전에 남가에 tumbu chen tumjo리샤섬 상로 망고단데 왜 가는 군두 제가 자도와 다 군두인게 디 거지 송두장 그 메시지 군두인게 데 삼던데 꼭 쉬우지 가보충 데 남게 뒤다 되저 콜라 데와데스 요서리시.
So if you are interested to know about space particle, then there's a story about David Finkelstein, one of the teachers who used to come and teach us. He told us that he was like constantly thinking about the space. So he thought that if there is a fundamental unit of time and fundamental unit of particles, then there has to be a fundamental unit of like very happy, knowing that he was not the only person who was thinking about the existence or maybe the possible existence to refer to the fundamental units of the space or like that. Laso gela number lenje so tuzu zobe ki chen che enanga zo ningung shela lunch break di shao keso ane ningung chusu ane niwala ya rangcha zumro chi sera ji shue du ane zidung ngam rikba de ngonyok ba da ting sabo ta dru bu chane ane dewa shukchen bu yunke yin ba songza dewa mangbu ane kera kind of thing then